Hello, we are going to start talking about inner product spaces. The main idea with an inner product is we're trying to generalize the dot product. So the dot product takes two vectors and outputs a number that somehow expresses how well the two vectors work together. That's how I think of it anyway. So we're going to do something similar with an inner product, where maybe our functions or vectors, whatever they are, it doesn't make sense. How about like dot the first and dot the second and multiply and add? So we say, well, okay, we still want it to be that we take two inputs and get a number output. What are the key properties we needed to follow? Here they are. So an inner product. We have any two vectors, u and v, that goes to a real number. And the rules are, first, symmetric. If we put u, comma v, or v, comma u, we get the same thing. And we use these little angle brackets, which is probably why the book uses parentheses for vectors, because it was saving angle brackets for the inner product. We have this additive property, which says if we can split one of the two vectors into u plus v, then we can kind of distribute the w to both of them. So we get uw, comma, or plus vw. We have a property called homogeneity. And what that says is that if there's a scalar for one of the two vectors, you can pull it out. Notice it only needs to be on one of them. If these both u and v were multiplied by c, you would pull them both out separately and it would be c squared in the front. So this is not a distributive property. This is saying a scalar that's assigned to either one of these vectors can be pulled out, or you could take it out and then put it back on the other one. And this is the positive definite rule. I should have written that at the end, which is the inner product of a vector with itself cannot be negative. And if you take the inner product with itself and get 0, the only way that can happen is if the vector itself was a 0 vector. So non-zero vector inner product with itself will give you a strictly positive number. And so a vector space with an inner product is called an inner product space. Makes sense? So what we're going to do is we're going to take some examples here, and we're going to show this is an inner product. So let's say we have vectors in R2, and we're going to define this operation. UV is x1, y1 plus 4x2, y2. So we multiply the first two, we multiply the second two, and then multiply that by 4, and then we add them both together. See, without that 4, this would just be the dot product. We're going to show this new version also qualifies as an inner product. So let's see how we do that. Well, step 1 would be the symmetry property. So we have x1, x2. No, hold on. Let's do this with the right notation. Vector is x1, x2. We'll do inner product with that and y1, y2. Well, that just by definition is x1, y1 plus 4, x2, y2. And I'll just do the other way and show that gives us the same thing. y1, y2, comma, x1, x2 is y1, x1 plus 4, y2, x2. But since these are real numbers are commutative, so we can just switch them around and we get the same thing. So that's a sufficient proof here. For part 1, I mean. For part 2, okay, we've got that additive property. So if we say x1 plus y1, comma, x2 plus y2, this is a vector, comma, z1, comma, z2. Well, following the rule, we get x1 plus y1 times z1 plus x2 plus y2 times z2. So then, again, now that we're just in real numbers, we can do whatever we want according to the usual rules of algebra. That's what tends to happen with these complicated structures. We try to reduce them down to something we already know how it works. Okay, we wanted to show that you could split into xz plus yz. So let's split up the x's with the y's. So we will get x1z1 plus, there was supposed to be a 4 here, wasn't there? I left off the 4, silly me. Yeah, it was supposed to be here. So 4, 4. Okay, so x1z1 plus 4 x2z2 plus y1z1 plus 4 y2z2, which this then becomes let's see, well, that is uw, where u and w were defined on the slide, uw plus vw. Or you could say it using the way we did before. You could say it as it's x1 z1. No, sorry, forget that. Yeah. So it meets property 2. All right, let's try property 3. So we want to show what is C, U, comma, V. So that is C of x1, x2, comma, y1, y2. Which becomes cx1, cx2, comma, y1, y2, which is cx1, y1 plus cx2, y2, which we can then pull the c out, c of x1, y1. I keep forgetting the 4, don't I? That's so silly. Don't make that mistake. x1, y1 plus 4 x2, y2 is c of x1, y1, comma, x1, x2, sorry. x1, x2, y1, y2. Okay, so the C that started inside was able to be taken outside. And for the final property, let's do the inner product of a vector with itself. Well, that would be x1, y, or x1, x2, comma, x1, x2. Which becomes x1 squared plus 4x2 squared. And well, squares can't be negative, so this has got to be greater than or equal to 0. And it can only equal 0 if x1 and x2 are both 0. So it fits that property too. So that's an inner product. So if you're asked to show this thing's inner product, you have to go through all of those steps. And then if we say, let's find an example, negative 2, 5, inner product with 3, 1, which would be negative 6 plus 4 times 5 times 1 is 14. All right. So now, our next example is with matrices. Now you can go through this, but honestly, it's very similar to the last one. We are going to define inner product as multiply each corresponding pair of terms or components and then add them all up. It's honest. This looks the same as the dot product. If we just wrote this in a row instead of as a matrix, it would be a dot product. So we can work our way through it. Let's show some of the properties anyway. Maybe I won't show every single one of them. Number 1, just the symmetry is pretty straightforward to show. Number 2. Okay, let's do number 2 here. So we want to show, let's define U as A, B, C, D. B as E, F, G, H. And I will define W as, let's use some Greek, alpha, beta, gamma, delta. So, U plus V, comma, W. Now, if we knew this was an inner product, we could just go ahead and split it up, but we don't, so we've got to show that. So, it's the inner product of A plus E, B plus F, C plus G, D plus H, comma, alpha, beta, gamma, delta. Which would then become A plus E, alpha, plus B plus F, beta, plus C plus G, gamma, plus D plus H, delta. And then distribute this, because they're real numbers. A alpha, let me do some colors here, plus E alpha, plus B beta, plus F beta, plus C gamma, plus G gamma, plus D delta, plus H delta. And then the black ones, that is the same as A, B, C, D, comma, alpha, beta, gamma, delta, plus E, F, G, H, comma, alpha, beta, gamma, delta. Which is exactly what we wanted. It's U, W, plus B, W. And you might have noticed we defined that we can split the first component this way, but since we also know that inner products are symmetric, we could also split the second component. You know, you would, if you wanted to split the second, you could just switch the order, split the first, and then switch the order again. So, same thing. I think I'm going to just leave the rest to you. If you want to work through them, you can. It's pretty straightforward. For number 4, again, you have to dot some, or not dot, but inner product something with itself, so you get a whole bunch of squares, which again would be positive. Okay. So for function spaces in particular, this is a good one because the dot product of a function is not something that makes a lot of sense. I mean, I guess you could dot the coefficients, but that doesn't really give you something very meaningful. Instead, what we do is we multiply them by each other and we integrate across some closed domain. In this case, 0, 1. We'll do 0, 1 for now. Sometimes we'll do minus 1 to 1. It'll be just generally just some interval that we choose to set at the beginning. That'll be given to you. You can't, once it's picked, it's an inner product. So you'd pick whatever makes sense for the problem you're dealing with. In this class, I'll just tell you what the interval is. So let's show that this is an inner product. Okay, on P2. All right, so since we're on P2, we will take an f and g, and let's see. The integral of f times g from 0 to 1 dx would be the same as the integral of gf dx. That's fg, and that's gf. So, yeah, you could, if my first instinct was to write all these out as like ax squared plus bx plus c, or a1 and ab2 and a3, or sorry, all three of them, and try to do it the long way, but we're allowed to say that certain facts from calculus we just know, and in this case we're just talking about regular multiplication. If I were to say f plus g comma h, this would be the integral 0 to 1 of f plus g h dx, which is integral from 0 to 1 of fh plus gh dx. And then we know integrals can split. The term, in fact, is that they are linear operators. Integral is a linear operator. We can split sums. So it works. And for in CF g is the integral 0,1 of CF g dx. Integrals are linear. Constants like c can be pulled out. As for the last one, what about inner product of a function with itself? Well, that would be the inner product of 0, 1 of f, all right, of x. I've been leaving out the of x part, dx. This thing is always positive. And because they're continuous, it can only be 0 if the function itself were 0. This is a trick here. The continuity was important because if we had like a discontinuous function, it might just have like a little jump up here that wouldn't change the area. But since it's a continuous function, if there's any spot where it's not 0, it has to smoothly go up there, and then we get some area. It becomes positive. So this will have to be greater than or equal to 0 because the inside is squared, and it equals 0 only if f is equal to 0 everywhere. Are what are called semi-norms, which drop out the rule that it'd have to be 0 to have an integral of 0 or a norm of 0, but we're not going to deal with them in this class. So let's find this particular inner product. Well, it must be the integral from 0 to 1 of x squared plus 2x minus 1 times 4x plus 1 dx, which is the integral from 0 to 1 of 4x cubed plus x squared plus 8x squared plus 2x minus 4x minus 1 dx. And you all know how to do integrals, so I'm going to skip to the answer, which is 2. Okay. Now, I used the term norm a minute ago, which we've talked about a little before with absolute values and such. But once we have an inner product, we can always define a norm this way. It is given by this double absolute value bar of v is you do the inner product of a vector with itself and then take the square root. And that's the same as we saw with dot product. We said if we do a dot product something with itself, we get the length squared. So then the square root to your root. So let's find the norm of f of x is 5x squared plus 1 with respect to the same inner product above, the integral from 0 to 1. So if we changed what the interval for the integration was, we would then create a new inner product. Okay. So we will have the integral from 0 to 1 of, let's put a square root on that, 5x plus 1 squared dx. Out to the integral from 0 to 1 of 25x squared, x fourth, no wait, sorry. Oh, yeah, there's a squared here. 25x fourth plus 10x squared plus 1 dx, which eventually works out to square root of 28 over 3. Which, if you want, you can mess around with this a little to change its form. Same thing. Yeah. Okay. So that's that. So yeah, the function spaces, this is stuff that I work with a lot, although I usually use a different norm than this one. But the concepts are still there. So, once again, we're just generalizing what we did with dot product. So, cosine theta, instead of u dot v, it's u inner product v over length of u, length of v, or norm of u, norm of v. So let's find the angle between these two separate functions, 5x squared and 3x. All right, so first thing we need, well, we can do whatever order we want, but I'm going to do the FG first. So that is 5x squared and 3x is integral from 0 to 1 of 15x third dx, which would be 15 over 4 integral from 0 to 1 of x to the fourth, which is 15 over 4. Now let's see. The norm of f would be the square root of f, which is the square root of the integral from 0 to 1 of 25x to the fourth dx, which would be square root of 0 to 1 of 5x to the fifth, which would be square root of 5. And the norm of g would be, g is, most people would save the square root till the end. They would work it out and then take the square root of it once they're done. So that's probably what I will do next time. Square root of 3. So cosine of theta would equal f comma g, that's 15 over 4, divided by norm of f, norm of g. Then become, we can rewrite this as 15 over root 15 times 1 over 4, which is root 15 over 4. And then to get the angle, theta is cosine to the minus 1 of root 15 over 4, which is right about 14.48 degrees. Okay. And so then we say, what else do we know? Well, we know orthogonality. Well, orthogonality, natural thing to say is that in Rn, it's when the dot product is 0. So in general spaces, it's when the inner product is 0. Let's show these two things are orthogonal. And again, this is a case where you really have to make sure you know what interval you're integrating over. Because some of the homeworks, it's minus 1 to 1 instead of 0 to 1. So just make sure you're paying attention to that. 0 to 1 of 3x minus 2 times x dx, which would be 0 to 1 of 3x squared minus 2x dx. 0, 1 of x to the third minus x squared. And we plug in, we get, well, 1 minus 1 is 0. Okay. So those are orthogonal in the function spaces. In P2, or really in any polynomial space, those would be orthogonal. So the distance. Now this is as general as it gets. Anytime you have a norm, the distance is going to be defined this way. I can't think of any exceptions to that, which is distance for u to v is you subtract the two vectors and take their norm. And so in inner product terms, that'd be u minus v, comma, u minus v, square root. And this actually has a tie-in with trigonometry I want to show you, which is, say we have a vector here, u, or length, it's length u, and length v. We got some angle theta. Then I'm sure we said at some point, but I'll reiterate, if we got two vectors and we subtract them, the difference is what connects their tips. So this, the length of this vector would be norm u minus v. So this is u, this is v, this is u minus v. So then as a triangle, these are their lengths, the lengths of the sides. Now we can say that u minus v, or let's say length of u minus v squared. That would equal u minus v, u minus v. Now we can use this distributive property, the additive property, it's the same thing. So we would say this would equal, let's split the first one, u minus v, minus v, u minus v, or wait, hold on, I'm saying something wrong here. I'm sorry. Let me erase that. I wrote that wrong. Trying to use the property here. It's what I meant to say was it's u comma u minus v plus negative v comma u minus v. And then we can split the second component as well. So it'd be u minus u b minus b u plus b v. And then we could say, okay, well, u, so that's norm of u squared minus, now because of symmetry, we can switch this one and combine like terms, 2u v plus norm of v squared. And then we can say, well, I know that u comma v over norm of u, norm of v would equal the cosine. So I can replace u comma v with norm of u, norm of v, cosine theta. So it'd be 2 u v cosine of theta plus v squared. And this is the law of cosines from trigonometry. It said the length of c squared, the side opposite the angle, is equal to the length of u squared plus length of v squared. If it's a right triangle, you could stop there and it'd be Pythagorean theorem. If it's not a right triangle, you have to minus 2 norm u, norm v, cosine of theta. So yeah, that's just showing a little connection between two different subjects. It's really, that's where the big revelations in math come from, is when you find two different things that seem unrelated but actually connect. Those usually called fundamental theorems. So, we have a function x squared. Which is closer? X squared minus 3x plus 5 or x squared plus 4? I would guess x squared plus 4 is closer because this one has an extra linear term and an extra constant, whereas this just has an extra constant. But we don't need to guess. We can prove it. So what is the distance from F to G would be the norm of F minus G, which would become F minus G would become 3x minus 5. And if you said G minus F, it'd be the same thing. You could show that using the inner product properties, that switching the signs on both of them, it would be like pulling a -1 out of both, so they would cancel out. So 3x minus 5, that would be the square root, and I said I would do it differently this time, but it's already set up, of 3x minus 5 squared dx. And then just do some basic integration rules. It's 13. And then the distance from F to H would be square root of integral of 0 to 1 of 4 dx. Or, no, hold on. 4 squared dx. Because we have to multiply. Yeah, let me add in the extra step that I skipped, just in case it helps clarify. Would be the norm of F minus H, which would be the norm of 4, which would be the inner product of 4 with itself, and then take square root. So that's square root of the 0 to 1 of 16 dx. That's just 16. So 4. Alright. There's one other type of inner product, and that's on complex numbers. If we have u and v are complex, each one is xi comma yi, we don't dot product them the same way we would with real numbers. For each case, we take the first part of u times the conjugate of the second v1. So this is just going to be C2 here. We just have two vectors. Each one has a complex number in the first, a complex number in the second. And so what this says is for each pair, we will take the complex number that's in u and the conjugate of the complex number that's in v and multiply those together. And so this, it has to do with orthogonality and a lot of other things, but this is just the standard way to define the inner product for complex numbers. So let's take these two. Let's find their inner product, find their lengths and their distance. Okay. So u comma v is 2 plus 3i negative 1 plus 5i comma 1 plus I negative I, which is 2 plus 3i times 1 minus I. So that's what conjugate means, in case you haven't seen it in a while. It is you take the complex number and you switch the sign on its imaginary part, but you leave the real part alone. Plus negative 1 plus 5i times the conjugate here would be 0 plus I, or just I. And then you work that out. You'll get, let's see, 2 minus 2i plus 3i plus 3 minus I minus 5. So let's see what the like terms are. 2, 5, 0, 3i, 1i, 0. Oh, 0. Oh, so these were orthogonal. These two numbers are orthogonal. The angle between them is 0. Okay. The length of u would then be square root of 2 plus 3i times 2 minus 3i. And so what that ends up as is just 4 plus 9, because all the, if you do the FOIL, the outer and the inner terms will be opposites, they'll zero out, and so you're just left with root 13. No, that's only the first part, isn't it? Back up. Yeah, that's only half of it. So let's back up. Square root of u comma u would be, let's do this properly, 2 plus 3i negative 1 plus 5i comma, or yeah, plus, or yeah. So for each term, you do the first times the conjugate of the second. So it'd be 2 plus 3i, 2 minus 3i, plus negative 1 plus 5i, negative 1 minus 5i. Which then becomes, yeah, the 13 for the first part, but the second part is 26. So we get root 39. For v, we would get, okay, so let's try that again. The norm of v is the square root of v comma v, which is the square root of, first one is, okay, so 1 plus I comma negative I, inner product 1 plus I comma negative I, which is square root of 1 plus I times 1 minus I plus negative I times positive I, which then becomes square root of 2 plus 1, or square root of 3. And then the distance from u to v is norm of u minus v, which is, let's see, norm of u minus v, comma, u minus v. Now, probably the best way to do this is to distribute it out like we did earlier, as you could subtract these directly, but I think it probably makes more sense to do this. U squared minus 2uv plus v squared. And then just use what we already know. The length of u was root 39, so this is 39 minus uv was 0 plus, and the norm of v was root 3. So this becomes 42. So the distance, this should have been, there was a square root on this whole thing the whole time. Distance squared is norm squared is times itself is this, and then the distance at the end is root 42. Yeah, like I said, it's usually people calculate distance squared and then just do the square root at the end, so that's kind of what we did here. Okay, so that's all for the inner product space, and I'll see you in class.